So, we've learned how to graph a lot of different types of functions this year, from linear to quadratic to absolute value, all these different types of graphs that we've kind of covered in our course together. Now, the last type of graph we're going to talk about this year is called a rational function. And rational, that word in general, when you hear it, typically, even though it's not like an official definition, we talked about what a rational number was. When you hear rational, in general, you want to think fraction. Rational functions have to deal with when you have fractions. Specifically, we have fractions involving variables in our denominator. That really hasn't happened before in your math careers. We've never really dealt with a situation like this, where we have an x in our denominator. So, anytime you're graphing something weird, obviously we can bust out our calculator and you can type it in and see what it looks like, and that's fine. But let's make a quick table right here. If you plug in a -3 for x, you get 1 over -3, which is equal to -1/3. Or you could write it as -0.333 repeating if you want to. If you plug in a -2, 1 over -2 is -1/2. 1 over -1 is -1. Now the interesting part comes in if you plug in a 0. 1 over 0 is not allowed. If you try typing 1 over 0 in your calculator, it's going to say error. Dividing by 0 is really, really bad. We cannot do that. This point doesn't even exist. We can't do it. If you plug in a 1, 1 over 1 is 1. If you plug in a 2, we have 1 over 2, which is 1/2. And if you plug in a 3, you have 1 over 3, like that. So if we actually go to plot some of these points here, 1, 1 is right there on the graph. 2, 1/2. We have 3, 1/3. If I were to do 4, I would have gotten 1/4. Really what I'm going to keep doing, if I plug in like a 50, I get 1 over 50. On this part of the graph right here, I'm just getting smaller and smaller and smaller and smaller and smaller fractions, but I'm never actually hitting 0. It's always going to be 1 over a really big number, which is a tiny, tiny decimal. On the negative side, if I plug in -1, I get out a -1. -2 is -1/2. -3 is -1/3. The same thing is going to happen right here. -4 is 1/4. It's going to keep going and leveling off like that. Now the interesting thing happens if you plug in, let's say, a decimal. Let's say I decided right here, for example, that I wanted to plug in x equals 0.1. If I do that, I would do 1 over 0.1, which is equal to 10. So I'm going to test it. What if I did 0.01? 1 over 0.01 is equal to 100. If I did 1 over 0.001, getting even closer to 0 right there, I can't actually plug in 0, but that equals 1,000. So anyway, what's happening here when we plug in really tiny decimals, our y is getting really, really big. So I'm going to erase all this. So key right here, if you plug in really tiny decimals, the y value is going to get larger, larger, larger. It's going to kind of go up like this. Never actually hitting 0, but it grows really quickly there. It keeps on going this way. Similarly, on the negative side, it's going to go down like this. So what we have here, after I put my arrows on the ends, is a really kind of a crazy-looking graph. We haven't seen anything like this before. It almost, if you tilt your head, looks like a bow tie. But we have 2 pieces to it. This whole thing is one graph. It's the graph of y equals 1 over x. Now notice, we're not allowed to have a point at 0. The graph kind of tails off in both directions at x equals 0. If you recall, that's a vertical asymptotes. So our graph has a vertical asymptotes at x equals 0 by default. If you look at that, it's at 0. Similarly, the graph levels off in both directions horizontally. So we have a horizontal asymptotes at y equals 0. So when we did our exponential functions, we had just a horizontal asymptote. Logs, just a vertical. Rational functions in general have 2 asymptotes. We have a vertical one, and we have a horizontal one. And there's one final comment here. If I were to do my domain and range on this problem, so we have our domain and we have our range. If you look at the domain, the x's keep going this way. They're going to keep going, keep going, keep going. So all the x's to the right are good. All the x's to the left are good. The only x that is bad is right there at 0. So the way I can show that here, instead of doing all real numbers, because it's not everything, I'm just going to say x can't equal 0. That pretty much implies that any other number you plug in is good. There's no 0. Similarly, on this problem, the range y does not equal to 0. And that is how you graph the most basic example of a rational function. That is actually called the parent function for rational. It's as simple as it gets in terms of nothing fancy going on. That's our parent function. In the next video, we're going to learn how we translate these and use the same rules that we've been using all along in this class.